Uh, Good afternoon, everyone. Welcome to today's class, that is lesson number 7 of module number 2. And we are dealing with the concept of compaction. A quick revision of the previous class. Uh, in the previous class, we learned about what are the different factors that are affecting the compaction. What are the factors that are affecting compaction, and what are the different effects the compaction has on the soil. Um, so the different effects of compaction were water content, amount of compaction, type of soil, admixtures, etc. And we also learned how the soil is affected by compaction. Like the density of the soil is going to increase after compaction, permeability is going to decrease, and um, I told you about what is wet side of compaction and what is dry side of compaction. Please remember this. This is very important. Okay, we have compaction curve. Okay, this is my y-axis and this is my x-axis. And please remember, always in a compaction curve, y-axis is dry density, x-axis is moisture content. And if okay, this is my compaction curve. And we'll take the highest point. The water content corresponding to the highest point is called OMC. And uh, the dry density corresponding to the highest point is called maximum dry density. Now, in the field, to achieve maximum dry density, the water content of the soil must be equal to optimum moisture content. Let's say if you are constructing a road and you want to compact the soil, then the water content of that particular soil must be equal to optimum moisture content if the soil should achieve maximum dry density. But uh, in most of the practical cases uh, in the field, the water content of the soil is not equal to optimum moisture content. Either it is less than optimum moisture content or more than optimum moisture content. Why? Because I told you about the different effects. Okay, like if the soil is compacted dry side of the optimum, compressibility will be more in the high pressure range. And if the soil is compacted dry side of optimum, it is going to swell more. And if uh, soil is compacted dry of optimum, its permeability will be more. Whereas if it is compacted on the wet side of the optimum, the soil is going to be less permeable and it is going to be more compressible in the low pressure range. Even an application of small pressure will compress the soil and it is going to shrink more and it will have lesser strength. And also on the if the soil is compacted on the wet side, more pore pressure, pore water pressure is going to develop. Okay, so you must understand what is the effect of compaction on the soil when it is compacted on the dry side and when it is compacted on the wet side. And always in the site, to achieve maximum dry density is not the only aim. Okay, we have to achieve more strength and sometimes uh, we have to achieve less compressibility and we don't want the soil to swell and we want less permeability, etc. Density is not the only desired, okay, parameter when we are working in the field. There are other parameters like permeability, compressibility, swelling, strength. Okay, we have to keep all those things in the mind and then we have to go for which moisture water content or the soil should have what water content, whether it should be equal to optimum moisture content, whether it should be on the dry side of the optimum moisture content, that is less than optimum moisture content, or whether it should be more than optimum moisture content. Okay, I'll give you an example. Okay, can you see this table? Okay, table dry side and wet side. Can you see this table? This is very important. What I'm talking about, it is a practical aspect. What is done in the field. Okay, I'll take first example. Okay, highway embankment. Now, when we are compacting highway embankment, okay, the water content that is maintained in the soil, it is less than OMC. Why? Because when the water content, when the soil is compacted on the dry side of the OMC, it will achieve high strength and it will have low compressibility and it will have good resistance to deformation. So if you are compacting the soil in the highway embankment, it is compacted on the dry side of the optimum. That is, the water content is less than optimum moisture content because we need the soil to have high strength and the compressibility of the soil should be low because if the soil compresses, the road above the soil will also get compressed and the road will get damaged. So when you're compacting soil for the highway embankment, it is compacted on the dry side. And also for earthen dams, high earthen dams, meaning big earthen dams, if the height is more than 10 meter. Okay. Now, when you're constructing earthen dams, the soil or the earth which is used to construct that particular dam, it is compacted on the dry side of optimum moisture content. Why? The main reason is to reduce the pore pressure development. Uh, there is less pore pressure on the dry side of optimum because the voids are not completely filled with water. Hence, the pore pressure will be less. Whereas on the wet side of the optimum, pores are completely filled with water. That's why pore pressure will be more. So in earthen dams, uh, we desire to have less pore pressure and that's why we compact the soil dry side of the optimum. uh, Less pore pressure is desired because water is stored on one side of the dam, and some water is seeping through the dam. If the pore pressure is high, that will lead to failure of the dam. That's why we desire to keep less pore pressure in the dam, in the earthen dam. So examples of soil being compacted on wet side: cohesive subgrades. Cohesive subgrades meaning if the soil is clay, when you are constructing a road, and if the soil is clay, we have to compact clay soils on the wet side of the optimum because we want to eliminate swelling. I showed you, okay, in the previous class. If the soil is on the dry side of the optimum, the swelling is more. Okay, so we want to eliminate this swelling. That's why we'll compact on the wet side of the optimum. So if the soil is cohesive, we are compacting on the wet side of the optimum. Next, in earthen dams, okay, there are layers: outside outside layer, inside core. Okay, we want the inside core of the earthen dam to be impermeable, or we want that core to have less permeability or low permeability, and that's why uh, we are compacting the inner core of the earthen dam on the wet side of the optimum. On the wet side of the optimum, the permeability is low because already the pores are completely filled with water, and the water cannot easily penetrate, or sorry, cannot easily flow through the voids, so it is less permeable. Hence the inner impervious core of the earthen dam, okay, it is compacted on the wet side of the optimum to achieve low permeability. So please remember, in most of the, okay, field, in most of the jobs, the compaction of when you are compacting soil, okay, the water content of soil is not exactly equal to the optimum moisture content, but sometimes depending on the desired, okay, function, the water content is less than optimum moisture content, that is dry side, or the water content is more than optimum moisture content, that is on the wet side. Now, yesterday we saw what were the factors that were affecting the compaction of the soil. There are some other factors which affect the compaction of the soil when we are compacting on the, okay, in the field. Okay, when we are compacting in the field, the factors that affect the compaction are placement water content, that is the water content of the soil which is being compacted. Second is type of the equipment for compaction, that is whether you are doing it with roller. There are different types of rollers: smooth wheeled, vibratory drum rollers, pneumatic rollers, etc. So the type of roller that is being used to compact the soil also has a major effect on the compaction of soil. Next is lift thickness. Lift thickness is, uh, let us say, I'll give you an example. Uh, this is my railway track, okay, and I'll just show the plan. This is the railway track, and this is the road. Okay, now this is my road. both are at same level. uh, the railway track and the road, they are at same level. Green color is road, and brown color is railway track. Okay, now let's say there is a lot of traffic on that road, and frequent railway crossings, they are closing the gate. So I want to increase the height of the road. I want to construct a bridge. So what I'll do, I'll keep the this is my uh, I will decide to construct the road at this level. Now the railway track is here. Okay, and I have decided to construct the road at this level. Hmm. So I cannot uh, take the road immediately at this level. I have to, the vehicles, okay, the road is here. It cannot come and the vehicles cannot come and suddenly jump on the road. So the elevation has to be increased gradually. This is the new road level. Okay, so this is my railway track. Earlier, the railway track and the road were at same level. Now, I have decided to increase the road level to this height. So, I will gradually start increasing the height. At this level, I'll just construct a slope. Now, the ground is at this level. So, what I have to do, I have to up to this height, I have to fill something, or I have to construct a bridge. I have to construct piers, and I have to construct a bridge. But more cheaper way is to construct an embankment. I'll fill this with soil. Did you understand this example? Anyone? The railway track is at this level. Can you see the screen? Can you see the screen now? Okay. The railway track is at this level, and we are increasing the height of the road. So I'll gradually increase the height of the road to this level. But my ground level is here, and my new road level is at this level. So the difference, I'm filling it with soil. So my question is, when I'm compacting the soil, okay, I'm compacting, let's say the height is 10 meters. Yeah, this height is 10 meters. Uh, I'm compacting 10-meter height of soil. So will I compact all the height at once, or I will do it in layers? In the compaction test, the complete mold was not compacted at once. Okay, we compacted it in, for standard test, we compacted it in 3 layers. For modified test, we compacted it in 5 layers. Here also in the field, okay, when you are compacting a certain height of soil, let's say 10 meter, you are not compacting the whole 10 meter at once. You are not filling the 10 meters of soil and you're okay, taking road roll over that soil mass. Here, when I'm compacting, I'll take layers of soil. I'll first compact the first layer, second layer, third layer, fourth layer. So this the 10-meter soil that is to be compacted, it will have at least 30 to 40 layers. So 10 meter is compacted in at least 30 to 40 layers. And the depth of one layer, it will depend on the type of compaction equipment that we are using. That is, the depth of one layer will depend on uh, uh, the roller that we are using. If it is a heavy roller, then we can then the depth of one layer can be kept more. If it is a light roller, then depth of one layer can be kept less. Usually, depth of one layer is around 15 centimeter to sorry 30 centimeter. Depth of one layer is around 15 centimeter to 30 centimeter. So that is my lift thickness. Lift thickness is the depth of one layer that is compacted. Okay, if you ask what is the lift thickness for standard Proctor test, it is one-third of the mold. It is compacted in 3 layers such that the depth of one layer is equal to one-third of the mold. Similarly, in the field, we are compacting in layers, and depth of each layer is called lift thickness. Next, and the last factor is number of passes. Okay, number of passes also depends upon type of soil and the equipment that is used. Number of passes meaning, uh, if I'm okay, this is my soil that is to be compacted, and this is my roller. If this is the length, one pass means the roller has to traverse from one end of the layer to other end of the layer. If this is the length of soil that is compacted, then this is one pass. If this if the if the road roller traverses from this end to the other end one time, then it is one pass. If it traverses back, then it is two passes. So number of passes is the number of times the roller traverses from one end to the other end of the soil. So these are the factors that affect compaction of soil in the field. Now, how to check whether proper compaction is done in the field. Okay. Let's say we are compacting soil, and some of the soil is taken to laboratory. The soil that is used for compaction, or the soil that is being compacted in the field, some sample is taken to the laboratory. Compaction test is conducted, standard test or modified test, and we are determining what is the maximum dry density and optimum moisture content. Then when the compaction is done in the field, let's say they compact one layer, let's say the depth of one layer is 25 centimeter. So after compacting one layer, we will take a sample, a core cutter sample. We will take core cutter sample, and we will determine its dry density, and we will determine its water content. Now you can determine dry density because you have taken core cutter sample. You can determine the dry density using core cutter method, or you can also determine dry density using sand replacement method. Okay, so dry density is determined in the field. Okay. Dry density is determined in the field, and it is compared to maximum dry density. Okay, we are calculating a parameter called as relative compaction. Relative compaction is equal to relative compaction is equal to uh, dry density that is determined in the field divided by of divided by maximum dry density of soil. So dry density that is determined in the field divided by maximum dry density multiplied by 100. Now let's take an example. Let's say maximum dry density is 2 gram per cc, and when the test is conducted in the lab, when we go to field, let's say we take a core cutter sample and we determine the dry density. Let's assume that dry density is 1.8 gram per cc. Now when you calculate a relative compaction, it will be equal to 1.8 divided by multiplied by 100. So relative compaction will be 1.8 divided by 2 is 0.9. 0.9 into 100 is 90. So relative compaction is 90%. The meaning is, although that soil can be compacted up to a maximum value of 2 gram per cc, in the field it is only compacted up to 1.8 gram per cc. Its capacity is 2, but it has only achieved 1.8. So it is achieving 90% of compaction. So this is relative compaction. And whether the proper compaction is done or not depends on this relative compaction value. For different civil engineering projects, we have different relative compaction values. Like for earthen dams, the relative compaction that must be achieved is 100%. For highway embankments, it must be 95%. So different projects have different relative compaction values. We conduct laboratory test on the soil and we determine maximum dry density and OMC. Then when the layer of soil is compacted, we determine its field dry density and then we calculate relative compaction. So that relative compaction must be greater than the desired relative compaction. So this is about the checking whether proper compaction is done in the field or no. Now, density can be determined using core cutter method. What about water content? Now, there are different methods to determine water content: oven drying method, calcium carbide method, etc. Oven drying method is a laboratory method and it takes 24 hours to determine water content. But if you want to determine water content quickly, we have calcium carbide method. Okay. Using calcium carbide method, you can determine the water content quickly. But if you don't have calcium carbide method, then you can go for another method, that is Proctor needle. So Proctor needle is an instrument used for rapid determination of water content of soil. Okay. Now, Proctor needle, it consists of a handle, calibrated stem, and it consists of a spring-loaded plunger, a needle shank, and a needle point. When you are compacting soil, okay, when you want to check whether the proper compaction is done in the field, you first do laboratory test to determine uh, maximum dry density and optimum moisture content. When you are conducting that test for the first trial, okay, you have to take this penetration needle and you have to plunge this needle and you have to try to penetrate into that mold of soil. It will give you the resistance force of the soil. So we know what is the water content of the soil when we are compacting the soil in the lab. So for the first trial, if the water content is 8%, for that, for 8% of water content, let's say the penetration force is 5. So we'll record for the trial one, water content was 8%. We'll record what was the penetration force of the needle. For trial 2, water content is 10.5%. Again, we will record the penetration force of the needle. For trial 3, water content was 12%. Again, we'll record the penetration force. Okay, you keep the penetration needle on the soil and you have to try to penetrate this needle into the soil, and it will give us the resistance force of the soil. So for different water content, we'll measure what is the penetration resistance. So for different water content, for the first trial, what is the penetration force? For the second trial, what is the penetration force? For the third trial, and so on. So we'll plot a calibrating curve. This is my calibrating curve. So this is my dry density. Okay, this is my water content. Here I'll take one more y-axis, and this is my penetration force. So for the first water content, what is the penetration force? For the second water content, let's say what is the penetration force? For the third trial corresponding to that water content, what is the penetration force? So you go on increasing the water content, the penetration force will decrease. So I'll get a calibrating curve. So this is my calibrating curve. I'll also get the compaction curve. They don't have any relation. So this is my calibrating curve. So I'll come to field. I'll take my proctor needle. Okay, that proctor needle is plunged into the compacted soil layer, and it will give us some resistance force. Now I'll refer my calibration curve, and I'll see what is the, let's say this is the resistance force given by the proctor needle for the soil compacted in the field. So corresponding to this penetration force, I'll see what is the water content. So this is the water content that is present in the field. So this is how you determine water content using proctor needle. Earlier it is calibrated in the field when we are conducting compaction test, and then after the calibration curve is drawn, we'll come to field, we'll plunge the needle into the compacted soil, and it will give us some resistance force, and corresponding to that resistance force, we'll find what is the corresponding water content from the calibration curve. So that is the water content of the soil in the field. You can use this method also to conduct to find out water content. So this is proctor needle. Next, now how to determine number of passes and lift thickness for compaction of soil. I told you what is one lift thickness. Okay, in the field we are not compacting the whole depth of the soil, we are compacting it in layers, and depth of each layer is one lift thickness. So generally one lift thickness varies between 15 to 30 centimeter based on the type of soil and the compaction achieved in the first 5 passes. Now, one can determine the number of passes and lift thickness by field experience. By field experience, or you can conduct a strip test. Okay, I'll explain strip test in the next class. But you can determine number of passes and thickness of one layer by field experience or by conducting strip test. Okay, just give you the table. Number of passes and thickness of one lift is very important when you're compacting the soil. If you go wrong in deciding how many number of passes and what should be the lift thickness, if you take lift thickness more, then the soil won't be compacted properly. If you take lift thickness less, then a more number of layers will be there, then it will be time consuming though. So you have to select a proper lift thickness. So based on experience, uh, this table gives you what should be the lift thickness for different types of soil depending on different types of compaction equipment. Let's say we have fine grained soil, that is clay or silt, and we are using a ship foot roller. We are providing a lift thickness of 15 and we are giving 4 to 6 passes. If we are using ship foot roller but the type of soil is coarse grained, again the lift thickness is around 15 centimeter but number of passes is 6 to 8. If we are using a rubber tire roller, lift thickness is 25 centimeter, we are giving 3 to 5 passes if coarse grained soil is, if the soil is coarse grained. And if the soil is fine grained for the same type of roller, the lift thickness is 15 to 20 centimeter and we are giving 4 to 6 passes. You can observe always for fine grained soils, we are reducing thickness and we are increasing the number of passes. Okay, for smooth wheeled rollers, if the soil is well graded sand, the lift thickness is 20 to 30 centimeter and we are giving only 4 passes. And for the same type of roller, if we have fine grained soils, the lift thickness is 15 to 20 centimeter and we are giving 6 passes. So this is just based on experience. Just go through the table, but please remember number of passes and lift thickness is very important. And some of the important points to take care is, see, the thickness of lifts is a very important factor in soil compaction because no matter how advanced the compactor is, the thick lifts, that is 30 centimeter, 40 centimeter lift, it cannot be compacted adequately. Okay, suitable lift thickness will reduce number of passes and hence improve production rates. Now, time is very important when you are constructing in the field. If you take very small lift thickness, then it is very time consuming. So we have to provide optimum or suitable lift thickness so that time is also not consumed more and also proper compaction is achieved. Now we can plot a graph between lift thickness and density to determine the lift thickness. Okay, we are providing, okay, we are compacting the soil in layers. So for the initial few layers, we can plot a graph. Let's say the first layer I'll give okay 8 centimeter thickness and I'll give number, take number of passes and I'll uh, determine its density and I'll plot the graph. But from the experience, the lift thickness varies between 15 centimeter to 30 centimeter. Now, as a thumb rule, okay, lift thickness, you can take lift thickness equal to 4 times the size of maximum aggregate. That is, when you do sieve analysis of soil, you can measure what is the highest size of the aggregate. If the highest size of the aggregate is, let's say 1 centimeter, okay, let's say 4 centimeter, you can take lift thickness as 4 into 4, 16 centimeter. So, as a thumb rule, thickness of lift is equal to 4 times the maximum aggregate size. Okay, sometimes okay the compactor or uh, the, the company which is providing the roller, okay, they will give a chart or table mentioning all the ideal maximum lift thickness. if the you should consider 75% of that value. If the lift thickness is 30%, you have to consider 75% of 30%, that is 23 centimeters. Okay. In case of large lift thickness like 30 centimeter, 35 centimeter, bridging may occur at the bottom of the lifts. Bridging means the layer may sag, and because of this sagging, it is going to cause problems. The road that is built upon this, it may also get settled, and cracks are developed in the road. Next, the number of passes required to obtain the required compaction. It depends on the lift thickness, the contact pressure that is applied by the roller, and the soil moisture content. So please remember, okay, and most of the compaction is achieved within the 5 passes. In the field, most of the compaction is achieved within the first five passes. Now, if you think that additional passes will increase further, will increase the density, it may or it may also have adverse effects. It may there cracks may be developed in the compacted layers. So always you have to give required amount of passes. No, you shouldn't give extra amount of passes because it may have adverse effects and cracks may be developed. So carelessness during the pass counts and coverage may lead to non-uniform compaction. Some part of the area may be compacted properly, some region may not be compacted properly. Now, and we are okay compacting the soil in layers. Let's say if you are compacting 10 meter of soil, usually you are compacting 10 meters in okay 30 to 40 layers. Now, the soil that is used in the each layer must be same. You shouldn't use different soil for different layers. If you are using different soil, then non-uniform compaction will happen, and this non-uniform compaction can be problematic for roads and structures. So this is about compaction in the field. So the very important terms that you learned today is lift thickness and number of passes. And we learned about Proctor needle, which is used to determine the field water content. And we also saw what is the significance of compacting the soil on the wet side and dry side of the optimum. Please remember, not all the soils are not compacted exactly at the optimum moisture content. Some of the soil, depending upon the desired function, soils are compacted either on the wet side or on the dry side. If you have any doubts, please ask. I hope the video and the sound was clear. There was no disturbance in video and sound. The PDF is sent in WhatsApp group. You can refer that. The things that were discussed in today's class, most of the things they are practical things. You won't find it in textbooks. So please go through the material and see that you learn about these things, how the compaction is done in the field. Uh, Tomorrow we'll learn about the different types of equipments or machineries that are used for compaction. Okay, that will be the last theoretical class of the uh, compaction. Next week we will start numerical problems. Okay, thank you. That's it for today's class. We'll again meet tomorrow at 10 o'clock. I have class at 10 o'clock, so we'll meet at 10 o'clock.